Hello students, in a new lecture of chapter 5 we're going to start to study the enthalpy of the reaction or heat of reaction, how we can get the value of heat of reaction and enthalpy of the reaction. By the first lecture we collected some information about the temperature, heat and specific heat and some other expressions. Today we're going to complete our informations in chapter 5 and starting from enthalpy of the reaction. Let's see what we have to do with the enthalpy of the reaction. Enthalpy of the reaction, there's another name of the enthalpy of the reaction, which is heat of the reaction. What is enthalpy of the reaction? It's the quantity of energy transferred as a heat during a chemical reaction. It's a quantity of energy transferred as a heat during a chemical reaction. So this is enthalpy of the reaction. There's another name of enthalpy, don't forget, heat of reaction. Heat of reaction, enthalpy of reaction, heat of reaction. And enthalpy change, delta H, is equal to, is the amount of energy absorbed or released by a system as a heat during a process at a constant pressure. The unit of delta H, enthalpy change, it's delta H, enthalpy is H. Delta H is measured by kilojoule or joule. Delta H at standard temperature and pressure, which is 1 atm and 25 Celsius degree. Oh, teacher, we've learned it. Standard temperature in grade 11 as a 0. Well, that was for comparing the property of gases. Comparing the property of gases, we should use standard temperature, but the standard temperature is 0 for comparing of gases. But for doing the reactions in the laboratory, the standard temperature is 25 Celsius degree. It's not practical to talk about enthalpy as a quantity. That's why, firstly, we have to calculate delta H. Then we can get the value of the enthalpy. So it means enthalpy cannot be measured directly, but delta H can be get directly. It means can be measured directly. The unit of measurement of delta H is kilojoule. You see, it's kilojoule simply. Well, dear students, I'll tell you the important thing. All the explanations in chapter 5 are very important. Well, you're going to face many questions in the final examination terms about the definitions in chapter 5. So they are very important. Memorize one by one very carefully. Don't confuse between them. What is the quantity of energy transferred as a heat during a chemical reaction? Oh, look, that's one that I talked about. Did you remember the explanation of enthalpy of the reaction? Is the quantity of energy transferred as a heat during a chemical reaction. So enthalpy of the reaction is the right answer. Which of the following cannot be measured directly? Again, enthalpy of the reaction cannot be measured directly. Enthalpy by change? No. I mean enthalpy of the reaction. I told you enthalpy, but I don't know why I haven't seen change. That's why enthalpy cannot be measured directly. So delta H is equal to the product energy minus to the energy of the reactant. It means H from the product minus H from the reactant. So there are two types of delta H, exothermic and endothermic. Exothermic releases energy, endothermic absorbs energy. Releases energy, exothermic. Absorbed energy, endothermic. Look, releases energy, exothermic. Absorbs energy, endothermic. So If the energy of the reactant is higher than the energy of the product, it's exothermic. But if the energy of the reactant is smaller than or less than the energy of the product, the reaction gonna be endothermic. Okay. In exothermic reaction, the level of the energy for the reactants is higher than the level of the energy for the product. So it's exothermic reaction. Well, it's too critical to identifying parts of this picture. This is energy of the reactant. Look, here we have energy. So energy of the reactants is very high, but energy of the product is very low. It means it releases energy. This is amount of energy. Amount of energy. It's amount of energy that releases. How we know it's amount of energy releases? We have higher energy, but now we get lower energy. So what will happen? What happened to the energy? What will happen to the energy? Will be released. The energy is released. That's why the energy of the reactant is higher than the energy of the product. There's a negative arithmetic sign for delta H. It means delta H is a negative. So the differentiate between them is the delta H. Delta H is negative. It means exothermic. Endothermic reaction is a chemical reaction that absorbs energy through a light or heat. Why? Because of the energy of the reactant is lower than the energy of the product. You see, here we have energy of the products at the higher level, but for the reactants, it's very low. So the difference between this amount, it's amount of energy that absorbed or released. Well, it looks like absorbed because of now we are in the higher level. So we absorbed something. Well, I'm not talking about myself, I'm talking about the reactants. Reactants are absorbed some energy to get higher energy of the product. So there's a positive symbol for delta H, it's endothermic. The energy of the product is higher than the energy of the reactants. Now we have a thermochemical equations. The thermochemical equations is a kind of equation that includes the quantity of energy with the reactant or with the products as written. It means we have some reactions, we have some equations, some reactions. For example, A plus B is equal to producing C. Okay, it's normal reaction. But what we call those reactions when they have quantity of energy as written with the product or with the reactants. We have 100 kilojoule with the reactants. So this is called thermochemical reaction. Look, thermochemical reaction, we have energy written with the reactants or with the products called thermochemical reaction. But if the energy is written with the reactants, the energy is written with the reactants, it's endothermic, delta H is positive. It's endothermic, delta H is positive. When? If we get the amount of energy written with the reactants. But if the amount of energy written with the products called exothermic reaction, negative delta H, positive delta H. 100 kilojoule written with the product, so delta H is equal to negative 100. Teacher, in here we have positive symbol, but why in here we have negative? Why here we just converted positive into negative? Well, when we write a reaction, how we can combine the components of the reaction? Of course, by positive symbol. By positive symbol. But it means the amount of energy that releases it. So it's exothermic. get out. Okay. Write each questions below with the delta H value included in either reactants or products. You see, for this reaction, it's exothermic. Exothermic, the energy must be right with the product or with the reactants. Of course, with the product. So the reaction will be 2SO2 plus O2 to producing 2SO3 plus 197 kilojoule. Why? It was negative, but now it's positive. No, please, don't say that again. Here, as I told you, combining reaction components, it's gonna be done just by positive, Another question, we have this reaction and put this amount of energy. This amount of energy, it's endothermic, so we're gonna write the energy with the reactants plus 114 kilojoule to producing 2NO times O2. It's very simple. Okay. Now we have some notes about heat of reaction, enthalpy change of the reaction. Okay, it's directly proportional to the number of the coefficient. It means increasing coefficient by 2, the enthalpy increases, decreasing, it will decrease. But before going to study those notes, we have something. A physical state, when you write a thermochemical reaction, a physical state must be mentioned, must be identified for the components of reactants and products, because of actually the physical state can influence the value of delta H. You see, here we just prepared a gaseous water, a vapor of water. Delta H is negative 242 kilojoule. But here we prepared a liquid water. Delta H is changed from 242 to 286 kilojoule. Now clearly we can see that a physical state can influence the value of delta H. That's why it should be mentioned: gas, liquid, or solid. Well, if the reaction is reversed, sometime we're going to need reversing some reaction to solving some question, especially during Hiss's law mathematical questions. We're going to reverse some reaction. So what's going to happen with the value of delta H? So we should reverse the arithmetic sign of delta H. Well, look. Combining carbon and oxygen to forming carbon dioxide, delta H is equal to negative 393 kilojoule. But if we convert, if you reverse this reaction, look, just convert and replace reactant by the product by the reactant. Well, we convert it. We reverse it. We just upside down the reaction. But what's going to happen with this value? Of course, it must be changed. Must be reversed. Negative, positive. Multiplying the reaction by any number, the value of delta H must be multiplied by the same number. Dividing reaction by any number, the value of delta H must be divided by the same number. Look, H2 plus half O2 gas to forming H2O. But let's multiply this reaction by 2H2, O2 to forming 2H2O. So the delta H must be multiplied by 2. It's not 4, it's not 3, it's 4, okay? It's very simple. We can see that 242 times 2 will be 484. 484. Well, what about the arithmetic sign of delta H? No, we did not reverse the reaction, so it's okay. We don't have any problem with the sign of delta H. We cannot convert it, but if we we cannot convert, we cannot turn it into other sign. But if we reverse, we should reverse the arithmetic sign of delta H also. where the value of enthalpy change is usually not significantly influenced by change of temperature. Now, the relationship between the heat of reaction and the number of mole, well, what's the number of mole? Oh, if you remember, the coefficient. We have 1 mole, delta H is equal to 2. If we increase by 2 mole, so 2 must be multiplied by 2. There's a relationship which is direct proportion. So, direct proportion relationship between delta H and coefficient in the reaction, it means number of moles. Enthalpy of formation. Enthalpy of formation, delta HF, is the enthalpy change that occurs when 1 mole of a compound formed from its elements. Look, 1 mole of compound, we should get 1 mole of the compound from the product. It's product. So, what about the reactants? Constituent elements or compound constituents which are elements in the reactant. So, during this conversion, the amount of enthalpy can be changed. So, it is called enthalpy of formation. When we prepare 1 mole of the compound from its free elements, from its what? Again, please repeat. From its free elements. So during this conversion, the enthalpy going to be changed, and we're going to call enthalpy of formation. Enthalpy of formation can be measured in unit of kilojoule per mole, because we just mentioned number of mole, which is 1. Well, how to write the enthalpy of the formation? Actually, we have too many things to study about the enthalpy of formation, the relationship between compound stability and enthalpy of formation, and how to write the reaction of the enthalpy of formation. It's very useful for the next lectures. Even for this lecture, it's very useful. Well, let's apply the definition of the enthalpy of formation. Enthalpy of formation says that 1 mole of the compound in the product. So 1 mole of CH4. What a cute CH4. Sorry. Well, we have to write 1 mole of CH4 in the product. Why? Because of the question says write the enthalpy of formation reaction. Write the formation reaction. Okay. Well, how many elements do we have in the CH4's formula? Carbon plus hydrogen. But about the gases, hydrogen, nitrogen, oxygen, chlor, fluor, brom, iod. They should write by diatomic molecule. By diatomic molecule. So that's why we have to write small 2 as a subscription in here. Now, 1 mole of the compound produced from its constituent elements. Next step will be balancing the equation, balancing the reaction, but don't forget that don't touch this number, don't touch that number 1. It should be constant. So multiply hydrogen by 2. Now they are balanced from both sides. C2H6. Okay, C2H6. We have carbon and hydrogen, which is H2. 2 carbon and for ethanol, it's a chemical formula for ethanol. 1 mole the compound in the formula OH. We have carbon, oxygen, and hydrogen. So just they should be diatomic molecules. Carbon is 2, 2. We have 5 hydrogen atoms. Well, don't forget that one. 6 hydrogen atoms, so it must be times 2, 3. Well, we have one oxygen atom in here, but here we have two oxygen atoms. So, well, multiply here by 2 simply. No, what I told you. Don't touch the coefficient for the compound. Instead of multiplying here by 2, multiply here by half. It's better. And it's safest way and it's correct. So, and these are your homeworks. Do that in your notebook and follow my steps. Well, let's talk about stability and the enthalpy of the formation. Simply, I'm going to explain the stability and the enthalpy of the formation, delta HF. If delta HF is a large negative value, the compound is very stable. Unreactive. But if enthalpy of the formation is less value, is small negative value, it means unstable. Or it means reactive. But what about if delta HF is positive? Well, it's super unstable. It's super reactive. It's very unstable. That's why, concisely, if we have large negative value, the compound is very stable. But if the delta HF is small negative value, compound is unstable. What about 0, where 0 is unstable? And positive is very unstable. So we have some examples about compound enthalpy of reaction, enthalpy of formation and stability. For example, ethene, such as acetylene, C2H5, has a very big number of delta HF, which is 226.7 kilojoule per mole. Oh, it's very big positive value. It's very reactive. It's very unstable, so it can react with oxygen violently, very fastly, just like the explosion. So it must be stored in a cylinder as a solution in an acetone. Why we kept acetylene in a cylinder contains acetone? Because of it's very unstable due to its large value of enthalpy of formation. Mercury fulminate. Mercury fulminate is it has a very large number of the enthalpy of formation. Well, again, it's very unstable, it's very reactive, so it can be useful as a detonator in the explosion to producing spark. Hydrogen iodide, HI, is a colorless gas that decomposes, and that's why the color to producing violet iodine vapor, because of its enthalpy is relatively high, positive value, enthalpy of formation. That's why, well, it's 26.5 kilojoule per mole. That's why it's unstable and it's reactive. Ethene acetylene must be stored in a cylinder as a solution in an acetone. Why? It's more stable? No, it's more unstable, highly unstable. And react violently with oxygen? Yeah, it's true also. So the right answer is D. Those compounds that have highly negative enthalpy of formation are okay. Highly negative enthalpy of formation, it must be very stable. So those compounds that have highly negative value of enthalpy, they are very stable. Highly unstable, no. Easily dissociative, no. More stable, or none of them. Of course, none of them is not correct because we have the right answer, which is B, more stable. So with this picture, I'll repeat to you. Here, enthalpy of formation, increasing positivity, so increasing instability, increasing negativity, increasing stability. So that's the figure of those explanation from the previous slide. Another enthalpy of the combustion, delta Hc, is the enthalpy change that occurs during the complete combustion of 1 mole of a compound. Well, we have a combustion of a compound, delta Hc. Enthalpy of combustion. It's always exothermic. When we burn something, it will give us energy. That's why it's exothermic. Well, you mentioned it, world of burning. Actually, there's a slight difference between burning and combustion. But because of our lecture is a quick and fast review, so I don't want to mention the difference between combustion and burning. But be aware that I mentioned that there's a difference between them. So I did not forget about the differentiate between burning and combustion. Well, even it's out of our book, our course book, so it's not important for us. Delta Hc is enthalpy of combustion, is the enthalpy change when 1 mole of a compound is completely burned. Well, about the enthalpy of formation, we put the compound from the product. But now we have to write from the reactant and then plus O2 to forming its combustible product, from its combustion products. The product of the combustion of reactions are compounds of oxygen called oxides because of, as I told you, we have to combine the compound with the oxygen to forming oxides. Carbon, when combined with oxygen, it will be CO2S with oxygen SO2, H with oxygen H2O, N with oxygen NO2. And O with oxygen, no, there's nothing like that. Well, a substance that contains hydrogen and carbon, or hydrogen and carbon and oxygen, the products are only CO2 and H2O as a combustion product. Then how to write a balancing combustion reaction? Before learning how to balance, we have to learn how to write the reaction. Then we have to think about the balancing the reaction. Now, write the combustion reaction for each of the following compounds. So first of all, write 1 mole of the compound from the reactant. 1 mole C2H2 plus O2 will be. Carbon with oxygen will be CO2 plus. Hydrogen with oxygen will be H2O. Okay. For C8H18 plus O2. Again, carbon with oxygen is CO2. Hydrogen with oxygen is H2O. Okay, teacher, now we've learned how to write a combustion reaction, but please tell us how to balancing the reaction. Well, first of all, balance carbon atom in both sides. Well, 2 carbons, we have to have 2 carbons. 2 hydrogens, 2 hydrogens. Hydrogens are equal. Then, how to balance the number of oxygen? We have to put some number in here to balancing the oxygen through this equation. Look. Sum the total number, make the summation of total number of oxygen in the product. Here we have 1 oxygen. Here we have 4 oxygen atoms. So it's 5. 5 oxygen atom. And then minus oxygen in the combustible compound. How many oxygens do you have in this formula? No. So it's 0. Divide by 2. We will get 5 by 2. So put 5 by 2 in here. 5 by 2. Well, for that one, 8 carbon atoms. 8 carbon atoms. 18 hydrogens. So write 9 in here. 18 hydrogen atoms. Then balance the oxygen. We have to calculate the number of mole of the oxygen atoms in here. Look. Total number of oxygen from the product, 2 times 8 is 16. 16 plus 9. 16 plus 9 is equal to what? 16 plus 9. It's 25. Okay? 2 times 8 is equal to 16. Here 1 times 9 is equal to 9. 16 plus 9 is equal to 25. 25 minus. Okay, 25 minus. How many oxygens do we have in this formula? No, we don't have any oxygen. So minus 0, divide by 2. 25 by 2. Okay, 25 by 2. You see that? The last equation, the last reaction that I'm going to show you how to write and how to balance that one. C2H5OH plus O2 to forming CO2 plus H2O. Good. Two carbon atoms, 6 hydrogen atoms. Total number of oxygen in the product is 4 oxygen plus 3 is 7 minus. How many oxygens do we have in this formula? 1 oxygen divided by 2 is equal to 6 by 2 is equal to 3. So we have to write 3 in here. Just like that, we can write a balancing reaction of combustion. بەم شێوەیە کۆتایی بەوانەی ئەمڕۆ دەهێنین. ئینشاڵڵا لەوانەیە داهاتوو دەست دەکەین بە چۆنەتی دۆزینەوەی گەرمی کارلێک وا ڕێگاکانی دۆزینەوەی گەرمی کارلێک و ئینشاڵڵا ئەگەر تەمەن باقیوی تا تەواوی کۆرسەکەی لەگەڵتان بەردەوام دەبم. تاوانێ داهاتوو بەخواتان دەست پێرم. خواتان لەگەڵ.